Hi folks. So I have a Hess's law problem to solve. So I will go through the question, I'll explain the question, and then we will try to work together to solve for the answer. Right. The question says, calculate the standard enthalpy change. I'll use my pen. So calculate the standard enthalpy change. That means we are looking for the change in enthalpy under standard conditions. So when we are using standard conditions, we use the circle on top to indicate that it's standard conditions. For the formation of one mole of strontium, carbonate, from its elements. The question also indicates that this material is used to give the red color in fireworks, but that is extra information. That information is not important for solving the equations delta H. Now, when we are given a Hess's law problem, they will give us a target equation. So our target equation, I'm going to label it as a target equation. This is the equation for which we are looking for the delta H. So what is the delta H, in other words, for this equation, where strontium, solid strontium, reacts with carbon, which is in the form of graphite, plus oxygen in the gas form. And the forms are very important in Hess's law. If it is a solid, we need a solid as a reactant. If it's a liquid, we need a liquid. And if it's a gas, we need to have it in the gas form. And this is going to be producing SrCO3 or strontium carbonate, and that's in the solid form, and we are looking for the delta H for this reaction. So the target is to find the delta H standard for this equation. Now, one way to do it is take the strontium, take the carbon, and use oxygen to burn it, and then you get SrCO3. That's a direct step, and you can also do this in small given steps. So they have given us three different equations that we can use to manipulate to get to this target equation. So the equations that they have given us, first equation is Sr, strontium, solid, plus half oxygen, and that's a gas. Usually you will have whole numbers. It is very rare to get a fraction in Hess's law, but in this case we do have one. And they have given us a delta H value for this reaction as negative 592 kilojoules, which is important to keep track of delta H values. Do not put them in later on. Put them or keep them in proper format, proper ratios, proper signs during the question. Do not try to put in the energies later on. Number one. Number two, Sr, strontium oxide in this case, solid, plus carbon dioxide, CO2, forms SrCO3, solid, and the delta H value goes to negative 234 or 234 kilojoules. And we have a third equation, which is carbon in the graphite form, plus oxygen, O2 gas, forms CO2 gas. And for this one also, the delta H is given as negative 394 kilojoules. So now we have three different equations, and now sometimes our students will get well, they'll get anxious because they have so many equations, so many variables in here. But what we have to remember is we have them labeled as 1, 2, and 3. And we have our target equation. What we need to do is we have to manipulate our equation number 1, equation number 2, and equation number 3 such that when we add these equations after manipulation, they will yield the target equation. And if we can make that happen, then the delta H values, the manipulated delta H values, will add up to the delta H of the target equation as well. All right, so that is our target, that is our objective here. Now, how do we decide how to manipulate our equation number 1, equation number 2, and equation number 3? Well, there's an easy way of doing this. You have to look for unique things that are in the reaction, the equations that are given to you, and the reaction. For example, I will start with the strontium, Sr solid. Look at that. We have Sr in the solid form, and we have one of it. In the three equations given to us, where is strontium? Well, I only see strontium in equation number 1. I don't see it in equation number 2. I don't see it in equation number 3. So that's the first step. So I know to get the proper number of strontiums, I have to manipulate equation number 1. Okay? So I'm going to manipulate here at the bottom, equation number 1. Now, how do I want to manipulate it? Is it on the left-hand side? Because in the target equation, strontium is on the reactant side. In my equation that I want to use, is strontium on the left as well? Yes, it is. So I don't have to flip the equation. So that's the first question I answered myself. The second question is, the quantities, are the quantities the same? I have one strontium in the target equation, one strontium in the equation number 1. So it is the same as well. So I will not manipulate the first equation. I will keep it as such. So I'm just going to rewrite here the same equation. I am not going to manipulate this. I am going to keep it exactly the way it is because it is in the format, it is in the proper quantities that I need this reaction to be. So the delta H value here is not going to be affected. It is going to stay the same as equation number 1. Now, I have finished working on manipulating with equation number 1. I will go to my equation number 2 next. What do I see unique? That is what I want to have in the products. I see strontium carbonate here, and the strontium carbonate is in only one equation, is in the second equation. Okay, so I know to balance or to get the proper number of strontium carbonates in my target equation, I will have to manipulate my equation number 2. All right, so let's manipulate that one. Equation number 2, I see strontium carbonate in my target equation is on the right hand side. In my target equation, and it's also in number 2, it is also on the right hand side. So it is on the proper side. So I don't have to flip this equation. Okay, second, the quantities, are the quantities the same? I need one strontium carbonate at the end. I have one strontium carbonate in my equation number 2 on the right hand side. So everything matches here. So I don't have to change my equation. I can keep it the way it is. So strontium oxide over here plus CO2 gas forms SrCO3 solid, and the delta H, since we did not manipulate the equation, we did not alter the equation in any form, we will have the same delta H value of negative 234 kilojoules. Alright, till now the question has been simple. We did not have to manipulate any of the equations. Let's look at the third equation here. Third equation, what we again have to look for is carbon in the graphite form If you see that, that is a unique quantity. There is oxygen as well, but the oxygen is present in multiple places. So I don't want to work with oxygen. I want to work with carbon, which is in the graphite form, over here. Because that's only present in one of these three equations, the third equation. Once I have that established, I can see the equation and see that there is carbon in the graphite form here. So first I will check, is it on the correct side? Well, in the target equation, it's on the left side. In this equation, also it's on the left side. So it is on the proper side. The quantity, I need to have 1, and I have 1. So that is perfect as well. So this question is pretty straightforward. Equations were already in the form that we wanted. We did not really have to manipulate any of the equations. But you have the idea now of as to how you would manipulate it. So you have the carbon in the graphite form plus O2 gas forms CO2 gas, and the delta H, again, since we did not multiply by -1, we did not flip the equation, and we did not multiply by a coefficient, it is the same as what we had before, 3 - 4 kilojoules. Okay, so we have our equation 1 in the proper form that we want, equation number 2, the proper form that we want, and 3 in the proper form that we want. We are not going to check for oxygen here because we are hoping that because we balanced, we have the proper amounts of strontium carbon and strontium carbonate, oxygens will be the proper amounts. But we need to check. So what we need to do is, now we will add equations. Till now you have been adding mathematical equations and so on. Now you will be balancing chemical equations here, or you will be adding your chemical equations. So when we add these chemical equations, the delta H will also add up. So what you can also do is anything common, in other words, anything that is present on the left-hand side and the right-hand side can be crossed out. So this, in a sense, is our dividing line. That's where the arrows are. Left-hand side are the reactants, right-hand side are the products. Anything that is common. So I see strontium oxide here and here. So that's gone. I see carbon dioxide, CO2 here and here. So that's gone as well. So what's left over? I cannot cancel anything else. So left over is I have a strontium, Sr, which is what I wanted. As you can see in the target equation, I have strontium. And then I have carbon left over. And it's on the left hand side, and I have oxygen. Now oxygen I have half plus 1, which is 1 1/2. 1 1/2 is the same as 3/2. So 3/2 O2, yes. Alright, which ends up same as the target equation. I am not copying the target equation here. I am adding the equations that are given to me on the left hand side, the 1, 2, 3, my manipulated equations, to see if I can get the target equation. So all of the reactants have been written down in my summation equation, and the only product that I get from all of these is SrCO3 in solid form. All the other products got cancelled out. They were, in other words, intermediates, if you want to think of it that way. We're going to talk about intermediates later on. So this is the equation. So what is the delta H value? Well, the delta H is the sum of the 3 delta H values that we had on top. You can say 1, 2, 3 if you would like. The delta H is equal to delta H of 1 plus the delta H of 2 plus the delta H of 3. So you have to take all the 3 values, which is negative 592, negative 234, negative 394 total kilojoules. And we can calculate the final answer. The final answer, and I'm just doing this on the calculator now, negative 592 minus 234 minus 394 gives me a value of negative or minus 1220 kilojoules. Alright, so 1220 kilojoules is my change in enthalpy. for this target reaction. And so that is my final answer for this problem. Right? So what have we learned? Again, we don't have to try to balance all the substances on the left hand side and the right hand side with the target equation. What you need to do is you need to pick unique things. So in the first equation, we picked strontium because that was unique. Because from all three reactions that were given to us, only strontium was present in the first reaction, and we had strontium in the target equation as well. So we can use that to manipulate equation number one. In the second equation, we identified strontium carbonate as something unique. So we used that to balance equation number two or manipulate equation number two. And for the third equation, we saw carbon in the graphite form as something unique. We did not pick oxygen because that was not unique to that equation. We picked carbon in the graphite form because that was unique and it would help us to easily manipulate the equation to get our target equation. Now, the number of equations given to us could be the number 2 equations, 3 equations, 4 equations, or even 5 equations. But the basic principles will stay the same. Your target, your objective is to get the target equation by manipulating the reactions given to you. And when you add them up, that should produce the target equation. And if it doesn't, then you can continue manipulating the equation in the two different ways I have indicated. Either you can flip the equation, in which case the delta H becomes -1 or multiplied by -1, and or you can multiply the entire equation by a coefficient. It could be a fraction, it could be a whole number. I hope you are able to grasp the concept of Hess's law and how to use Hess's law to solve problems.